Hi, it's time for another math easy solution. Time to discuss further into partial fraction decomposition, and now just go over a summary of the earlier videos I did, and also a brief explanation of the higher powers. Basically, in my earlier videos, I went over the proof for the partial fraction decomposition of the simple linear cases, and you can see those videos in the link below. I'll go over those right now. But for before I get to those, basically for the following theorems, just assume these following rules right here. N and D are polynomials where degree of n is smaller than degree of d, or in other words, we get a proper fraction. You can see more about this in my earlier videos on partial fraction decomposition. And also k is just a constant, and now here a1 all the way to aj, these are all different constants. They could be 0, it doesn't matter. And now m1 all the way to mj are just positive integers like 1, 2, 3, 4, also n1 to nk. And also right here, these terms x squared plus b1x plus c1, and then all the way to x squared plus bkx plus ck. These are all different when you look at these factors. Consider these all different. So now the simplest case, which I proved in my earlier video, is basically linear factors that don't repeat. So this is the one we went over. This was when you have something like this, where 3x plus 2 divided by x plus 1. So as you can see, these are all linear factors. It's an x, there's no x squared or x cubed, etc. And then this one, it becomes like you have a number right here, 2 over x plus 1 over x squared, or writing this in generally, n of x divided by x minus a1 times by all the way until you get the most general, x minus aj. In this case, you have a minus 0, and then you have a minus a negative 1 here. That's the plus. And then you get constants a1 all the way to aj, and then you just divide this by each factor. So that's the simplest case, which I proved in my earlier video. And now the general case is when you can have linear factors that repeat. I forgot here this k here. So this one works even if we put a k constant. It doesn't matter here. It's just like initially that was just a 1. You could have this a 2, 3, 4. It doesn't matter. Just the only thing that will change is these constants will change. So now when we look at the general case, I also proved this in my earlier video, linear factors that do repeat. So now we have an n over x, the same thing. Now we have these linear factors, but now you have to the power of, well, like m1. It could be 1, 2, 3, 4, 5, doesn't matter. And then all the way you keep multiplying, and let's say each one could have a different power, so up to mj. So then the way we would do this is just, this will be constant, so we would separate this for each one right here. So we'll have factor here, a constant here, a1 or coefficient a11 divided by x minus a1, which is the first factor to the power of 1. And then this is a1 now all the way to m1 power, and this is divided by, well, m1 power. So we have all these coefficients, and we keep doing this until we get to this term, and then we get this term right here, aj1 power of 1, so these ones line up all the way to mj right here to the power. And one example is this one here. I did x squared plus 1 divided by x times x minus 1 power of 3. And then we get, well, negative 1 over x plus 1 over x1. And then in this case, there's a 0 term, so that's why there's no x minus 1 squared. So now we have a 2 divided by x minus 1 cubed right there. Yeah, so basically for each power, we need to have a factor, a partial fraction, x minus 1, x minus 1 squared, and x minus 1 cubed. So in this case, there's a 0 term for the x minus 1 squared. So we had a 0 over here. And I did this also in the earlier video. And now if we go over the simple linear and quadratic factor case, which is just a combination of non-repeating linear factors with non-repeating irreducible factors of degree 2. So in this case, we're not dealing with just linear but also non-linear power of 2 polynomials. And the proof for this is similar to proofs in my earlier videos, but much more tedious, so I will not cover them anytime soon, but maybe sometime in the future, because my earlier proofs on the simple ones took like a half an hour or so. These kinds with the non-linear will take just even longer. I might do those later. And so as you can see, the general form, we write it down, n over x, k, that's constant, times by, well, this is the linear part, and now you have this x squared plus b1x plus c1, this is the non-linear part, all the way until we get the most general one, x squared plus bk plus times x plus ck. And now and what they equal as well, we write it down here. This is the same thing we covered, it's the linear case. And then all of a sudden we have the nonlinear where we have to add a b1x plus c1 right here. And I explained briefly why this had to be like this in my earlier video on nonlinear factors, but it didn't go over it too well. I'm not going to prove this, is just going to be more tedious. I might prove it later. So as you can see here, so we have two parts, the linear, and then a nonlinear. We have to account for each one. So there's the coefficients b1 and c1, and then there's a bk up to ck inside, so there's an x there. Now, and one example is right here, x minus 3 divided by x times x squared plus 3. So this is nonlinear, linear. Now we get the partial fraction of a negative 1 over x, which is, let's say, the first part, and then the second part, x squared plus 3. That is a nonlinear factor, so then there's an x plus 1. So in this case, our b and c are both 1 in this case. And now when we go over the general linear and quadratic factors, I'm also not going to prove this. This is just even more tedious. It's a combination of repeating linear factors with repeating irreducible factors of degree 2. So here's the same thing. Also, I'll put the k here. So just a random coefficient or constant. So now we have an x plus a1 power of m times it by, and then we keep going on and on until we get x plus aj times m power of j, m power of mj, and then we times it by, well, now we do the nonlinear part right here, and then we have to include n1 all the way to nk, so different powers for these ones. And now we're gonna do, what we're gonna get here is, it's basically similar to the general case for the simple linear ones. We for the linear factors here, we're gonna have to include coefficients for this x plus a1 power of 1 all the way to x plus a1 power of m1. So we have different coefficients for each linear factor and power of linear factor all the way to now we get to the final multiplication final linear factor, which is the power of mj, and then we can do this for each case of it, where it's power of 1, 2, 3 all the way to mj and different coefficients. And also now for the non-linear case, same exact thing. So this is showing for the first factor, and then we do it for power of 1 all the way to power of n1 right here. We keep adding it, so we'll have different factors, b11, c11, all the way to b1, n1, c1, n1, all the way up to k. And now we have bk1, ck1, now bk, nk, and this is the last factor, but there's a power of nk, so we have to include power of 1, 2, 3, etc., etc. And now one example is right here, x4 plus 3x minus 2. And again, this is a degree 4 at the top. Remember, the degree has to be less than a degree at the bottom to be proper. So this is going to be, well, x squared plus 1, that's a non-linear, power of 3. So eventually this is going to be x squared power of 3, that's 6. And then there's a squared right here, so this is a power of 8 right here, degree 8. So this is a proper fraction. And right here we have a linear case, power of 2. So we have to go, well, ax plus b, x squared plus 1, a power of 1, 2, and 3. So we have to include the nonlinear factors. And then for the linear one, just g and h, which are just two coefficients for x minus 4 and x minus 4 squared. So this is just a general way of writing it for all cases, and this is a simple example. And now basically, there are similar theorems for factors of higher power polynomials, and I'm not going to go over those. Those are just way more intense. Instead of using this for, let's say, if it's x, for degree 3, we would have to have on the top a polynomial degree of 2 right here, as opposed to 1 right here. So but for degree 5 or higher, this is interesting. The 20-year-old French mathematician Evariste Galois, actually there's an O in there. Let's put the O. So that's how you spell it, I think. It's something like that. And he proved that the simple general formulas that we just showed over here for these cases do not exist for powers of 5 or higher and cannot ever be found. I'm not going to go over that proof. It's pretty intense. And also some interesting notes on this Evariste Galois. He was a really bright kid. He lived from, well, October 25th, 1811 to May 31st, 1832. So he basically died when he was 20 years old. And in his teens, he was able to form several important proofs and theorems in advanced mathematics and algebra. So you can Google his name, check on Wikipedia for him. It's pretty advanced. Also, he was a political prisoner during the political turmoil in France. He was involved in some protests and other stuff. And the most interesting part about him is actually his death. He died during a duel where I guess two guys walk backwards and then they turn and shoot each other with a gun. Yeah, it was just ridiculous back then. Anyways, the reasons for the duel have not been fully discovered, with many possible theories presented, with some pointing to letters that he even wrote shortly prior to his death about a broken love affair, and also it could have been political reasons and so on. Anyways, that's all for today. Hopefully you learned from this pretty intensive summary on partial fraction decomposition. Yeah, this is a pretty intense field. It's a lot of algebra and theorems involved. Anyways, that's all for today. Hopefully you learned from this, and like always, you could download these exact notes in the link below, and stay tuned for another Math Easy solution.